So with these properties of logs, okay, we're going to be condensing and we're going to be expanding. But what we're trying to do is this. We're trying to write an equivalent expression. Right? Equivalent means the same thing. So mathematically, if you plug in a number into both of your equations, theoretically you should get the same number out, right? The same value, as long as you quote unquote do the math right. So we have two properties to begin with. Our product property, meaning we start with the log of a product, right? Two or more things are being multiplied together. Okay, so if we have multiplication of logs, we can write an equivalent expression by adding those two logs together. Okay, so if we ever see the log of a product, we can change that into the sum of logs. Okay, it also works the other way if we were going to be condensing. Okay, so then we're going to be condense. This way is expanding. If we ever want to have more logs, then we are expanding. If you want to have less logs, we are condensing. Okay, we're going to be condensing when we actually solve logarithmic equations because there's some properties that we're going to apply when we solve them. So if we have multiplication, that becomes addition of logs, and vice versa. Addition of logs becomes multiplication. Okay, and then if we have division, division of logs when we expand becomes subtraction. Okay, and then we can go backwards if we're asked to condense. We take the subtraction and change it back into division if we're going to be condensing our logs. So let's use these properties and condense. Okay, write as a single log expression. That means the log of just one thing. Right? One log, one word log in our expression. So I start off with what operation? Plus. I start off with plus. And plus becomes what operation when I condense? Becomes multiplication. So that's going to be 4 times 8, right? I'm multiplying their arguments together. So log base 2 of 4 times 8. That's what our property says. If we are adding two logs together, that's the same as taking one log of their products. So then what is 4 times 8? 32. So we can write it as a simplified log, log base 2 of 32. So notice that the bases always stay the same. And the bases have to be the same in order for you to be able to condense these. Right? If we have different bases in our logs, then we can't condense them because those aren't the same thing. Okay? So here we have addition. Once again, addition becomes multiplication. And we're going to multiply our two arguments together. So we have 1 log base 2, and then we have in parentheses 3x. Okay, so you might not see it in parentheses, but then again, you might see it in parentheses, and it's always okay if you put it into parentheses. Okay, we have two operations here. We have addition and we have subtraction. So what do we do first? First, we change our addition into multiplication. Okay, we're going to do the product property first. So we're going to multiply our two arguments together, which are x and y. So log base 2 of x times y minus log base 2 of z. Okay, so first we condense by changing addition to multiplication. Now we're going to do our subtraction and change subtraction into division. So the thing in front of the minus, our x times y, becomes your numerator, and the thing after the minus becomes your denominator. So 1 log base 2 of x times y divided by z. Now we're taking this one, which happens to be a multiplication problem, right? These are being multiplied, And how many things are being multiplied together? 2 of them. So we're going to have how many logs? We're going to have 2. Okay, because you have 1 log for every term, basically. So we have log base 5 of 4, the first term, plus log base 5 of x, the second term. So here we also have 2 terms, and our log base is 7. So log base of 7 and log base of 7. Well, division becomes subtraction. Okay, so it's the log of the top, which is 4, minus the log of the bottom, which is x. So log base 7 of 4 minus log base 7 of x. Okay, our last one. How many log arguments do we have? We have 3. We have a numerator and we have 2 things in the denominator. But first, we get rid of division. So we take our division and we write it as subtraction. And now we have this multiplication going on over here. So we're going to change our multiplication into addition. So now if we want to get rid of parentheses, that means we have to distribute this minus into here also. Okay, so once we do that, if we distribute that minus, then we have log base 7 of 4 minus log base 7x minus log base 7y. Okay, example 2, we're trying to relate a horizontal dilation with a vertical translation. So notice anytime you have a number inside of your parentheses affecting x, that is a horizontal type of a transformation. In this case, since it's being multiplied, it's a horizontal dilation by a factor of 1/6, because parentheses always lie. Well, they want us to write it as a vertical translation, right? Some other function g plus the vertical component k. And it's not hard to do. We're just going to use our properties of logs, which says addition of logs, or rather multiplication becomes addition. So I can have log of 6 plus the log of x. Right, I can change my multiplication of 6x into the log of 6 plus the log of x. Well, this is your g of x function right here, right? This is our function. And the log 6, this is a constant. So I know it doesn't look like a constant because we're not too familiar with logs and their decimal equivalents. But log 6 is a number. It's a number between 0 and 1. So this is, in fact, your constant that has been vertically shifted log 6 units. Whatever your calculator says that is, that's the vertical shift of your graph for log of x. Okay, let's talk about our third property, and that's the power property. So if your argument has a power, we can instead move that power to the front as a multiplication problem. So we are multiplying our log by a number rather than raising the argument to a power. Okay, so let's see what that would look like in amongst all these other ones. So option A here, or rather example 3A, we simply want to take our power and move it to the front. So this is equivalent to 3 times log base 5 of x. Okay, for option B here, notice we have a product. So the first thing we have to do is change our multiplication into addition. Now that we've done that, we can now take our powers and move it to the front of each individual log. So that's 3 times the log base 5 of x plus 2 times the log base 5 of y. So part C here, we have the log base 3 of x squared divided by 9y to the 4th. Okay, so the first thing we're going to do is we're going to take our division, change division into subtraction. Okay. So now let's change our multiplication into an addition problem. So here we have some multiplication. So that's the only thing that's going to change in this next part. So we put everything after the minus in parentheses because right, everything in your denominator needs to stick together. So all of this stuff is in our denominator, so it gets parenthesized. But now that we have everything separated, we can take our powers and bring it to the front of the log to which it belongs. Okay, so log base 3 of 9 is not going to have a power because it doesn't have one to begin with. So this would be your final equivalent expression. Okay, with no powers, with no multiplication, and with no division. So now let's go the opposite way. That means we're going to take our 5 and write it as a power. So log of y to the 5th would be this one's equivalent expression. Okay? Oh, when there's multiple, the first thing we do is change our multipliers into powers. Okay? So this is log base 7 of x to the 10th minus log base 7 of y cubed. Okay, that's the first thing, is to change your multiplication, right, your scalar in front of the log to be a power of whatever your argument is. And now we're going to change subtraction into division. So this is log base 7 of x to the 10th over y cubed. And that would be your final equivalence expression. Okay, here's another relationship between vertical dilations and powers. Okay, so vertical dilation, notice a vertical dilation is where we have a number, I don't know, it's not a 2, but a number times the function. Right, this part right here is your vertical dilation piece. Okay, so we're going to take and apply this property of powers and bring our 2 to the front. So g of x equals 2 times the log base 2 of x. Well, I have named log base 2 of x, I've named that f. Right, so f is known as log base 2 of x. Which means log base 2 of x is also known as f. So sure enough, when I use this property, I find that it is a vertical dilation of my original function. Right? The 2 as the product in front is where you're going to find your vertical dilation. Okay, so our final property is this change of base property, which was important before the advent of powerful computers because we had to figure out what the bases were and use our abacus whenever we were doing these kind of things. So notice what's happening. You can take the argument, that goes in your numerator, and the base goes in your denominator. And the, I won't say cool part, but you can take whatever base you want of the top and the bottom. As long as you take the same base, it is an equivalent expression. Okay? This property illustrates that all logarithmic functions are vertical dilations of each other. Of course they are. Okay, so change it to base 10. So this is your numerator, right? This is going to become your numerator, and your denominator is going to be 3. So what does log base 10 look like? Well, that's log without a base, right? So if you don't see a number after the g, a subscript, that's log base 10. So log base 10 of x over log base 10 of 3. Log x over log 3. As long as the bases are the same, that is an equivalent expression. So over here, we want to change it to base 2, right? Which is a perfectly fine thing to do, which just means we have log base 2 on your numerator and your denominator. Okay, that's the only thing that changes is the subscript of your log. And that's still an equivalent expression. So let's see if we can apply that property to here. Describe the relationship between log base 5 and log base 125. Okay, which is kind of hard to do. So let's do some equivalence. So if I had log base 5, what is its exponential inverse? So the exponential inverse has the same base as your log, but it's raised to the x power. Okay? So my inverse of log base 5 is 5 to the x, which means the inverse of log base 125 would be 125 to the x. Okay? So because I don't really understand a whole lot about logs, right, I'm going to change both of these to something that I do understand. I understand exponentials way more than I understand logarithms. So I'm going to change this to something I understand and then make some other connections that we've already made. So in order to really compare apples and apples, I need to change 125 to have a base of 5. So 125 is 5 to the what power? Well, that's 5 to the third. 5 times 5 times 5 is 125. So now that I have the same base, I can compare my two equations. Right? And what do I notice about my exponents? Right? This one is x and that one is 3x. And anytime something happens with an x, this is a horizontal transformation. Right? In fact, this is a dilation because it is being multiplied by your x. Okay? Now, that's true for my exponent. Okay? That's true for my exponent. Then my exponentials, the 125 base, is a horizontal transformation of my 5 to the x base. So if my exponential is a horizontal transformation, what does that say about my inverse, the logarithm? What's the inverse of a horizontal transformation? That would be a vertical transformation. Okay? So log base 5 and log base 125 are vertical dilations of each other. So if I were to do a little sketch, so watch me do this sketch. Okay, log base 5 looks like that. Where log base 125 looks like this. Okay? It is a vertical dilation of your original function. That's the relationship. Okay? So if you're asked questions about logs, sometimes it's easier to look at the answer as an exponential. Okay, have fun with these. They're amazing.